this next topic we're going to take a look at is, again, probably a number of different concepts that you've seen in your Stats 1 class or some other basic statistics class that you might have taken before. We're just, again, going to be looking at how do we implement some of these basic statistical measures in Excel and thinking about it from a business perspective. So again, very big intro stuff. This shouldn't take that long. We've got to review the concept of population versus sample. Again, that's probably something that you're familiar with, right? Our population is the entire group, and a sample is just some subset that is taken from that larger group, right? And so we've got a number of different methods that your book goes through that talks about different ways that we can try to do samples. A good sample is going to be one that's representative, right? And sometimes in order for something to be representative, it's a little bit difficult to acquire that subset of our population that's representative. And so we might have to do some different statistical techniques that are beyond this class that try to make it look a little bit more representative. But fundamentally, right, we want to draw this distinction between a population, which is the entire group, and the sample, which is just a subset. And most of the time, right, for cost reasons and for convenience reasons, we're going to be dealing with a sample. It's good when those samples are reflective of the overall population. If not, then there might be a little bit more uncertainty about what's going on in our sample values. And so throughout this whole topic, we're going to often draw a distinction between some of our measurements that are population measures and some of our measures that are sample measures. And that's going to be a consistent theme, not just in this topic, but in some later ones as well. We start with our measures of central tendency, and again, pretty basic concepts. I just want to make sure that we understand some of the terminology and some of the notation here, right? We're the mean or the average. You know these, right? More than likely you've seen these a number of different times. But again, we're differentiating between a population mean and a sample mean. On the right-hand side, we've got some notation that I want to make sure we talk through, right? The book uses this convention, and other internet sources are going to use this convention as well, that they use Greek letters to represent population values, and then we use our more common letters to represent our samples. Another common set of notation that you may see is a mu, right? That Greek letter mu by itself would represent a population value, and if you put a hat on it, that would represent a sample value. That's another common notation that you might see sometimes. But again, we're going to follow the traditional X bar and Greek symbol mu, right? Notice that these equations look very, very similar. We've got in red, we've got the summation, right? So we're going to add up a bunch of different values. And again, summation notation works. Our I is our indexer, where it's starting we index that value starting with a 1, and we increase by 1 unit increments until we get to the ending value, which is cap n. Cap n is the total number of observations in our population, right? So we're just adding up the values of x. That's all that fancy notation is just saying. And then we take that summation of all the different values of x, and we divide by n, the total number of observations, population. You know how to do the average, right? Add everything up, divide by the number of observations, that's the population mean, right? So the sample equivalent of this, the sample mean, is again the summation, but now the only thing we're doing is we're just changing from cap n to lowercase n, where lowercase n is the total number of observations in the sample, right? So we total the total number of observations in our sample, divide by n, the number of observations in our sample. Either of these population means, again, it tells us a whole lot about our distribution. It doesn't tell us everything, but it's one of the most common measures of what we call central tendency, right? It's very much one of our first starting places when we think about what does data look like, to talk about what the average is. Some other common ones that you're familiar with: mean, median, mode. And real quick, just as a refresher, tell me what mean, median, and mode are, the difference between them. Right, so the mean is a pretty straightforward calculation, but it of course can be influenced by outliers. And so a great example of this is we've got a number of Super Bowl wins for 5 different individuals. 4 of those are at Ohio Northern University, right? There's me and a couple of other people, and I also included Tom Brady in this list. And what, 5 plus 0 plus 0 plus 0 plus 0 is a total, right? The summation of all of these Super Bowl wins is 5 divided by the number of observations, 1, 2, 3, 4, 5, divided by 5. On average, there is 1 Super Bowl win per person here. Yep, clearly that's influenced by outliers, right? And so maybe you might want to think about what's the median of this group? What's the mode of this group? All of those are different ways that we can very succinctly talk about what we call our central tendency of the data, but mean is the most common one that we do, right? Another way to illustrate where the mean or the average might not necessarily capture something with more of a business application, right, is what I've got here is I've got a nice little graph here from Fred, from the Federal Reserve, where it's just pulling the data across a given timeline of average, mean, personal income in the U.S. The average personal income in the U.S. 2016 was a value of $46,550. Pause for a second and tell me, do you think that that value seems a little high to you, or seems a little low to you, or does it seem just about right? Remember, how would we calculate something like this mean personal income? We'd be measuring the total income of everyone in the U.S. divided by the number of people in the U.S. Does everybody earn an income? They don't, right? And so maybe for that reason you thought this number seemed a little bit high or low, right? This is not looking at household income, but rather this is personal income, right, per person. So again, that 46,000 very much influenced by outliers, right? In a little bit we're going to talk about the shape of what the income distribution might look like. Mean personal income, we see it all the time in data. It's still useful, but it's not capturing everything, maybe not be capturing as much as what a median measure of personal income might be doing, again, because it's being influenced by these outliers. We'll come back to that concept in a second. So first we understand kind of like where the center of our data is, this measure of central tendency. And the second place that we go is we measure of dispersion, right? So we're thinking about how spread out my data is. That's what these next few set of measurements are going to be looking at, right? So a number of these, again, you've probably seen them before, but just as a quick review, the range, the IQR, variance, and standard deviation, right? So the range and the IQR, I think of those two as going hand in hand. What's the difference between the two, right? So what the range literally is measuring is simply the maximum value in your sample minus your minimum value in your sample. The range just tells you, right, the difference between the max and the min. And again, if you've got some outliers, that might really skew this value of range that's supposed to be telling you about how spread out your data is. And so a way to kind of adjust for having some outliers in your data is to have this concept of the IQR, or the inner quartile range. It's got three parts to it, right? Quartiles, right? Do you know how to calculate a quartile of something? If we have a bunch of data and we just split it in 4 pieces, right? Those are called quartiles, right? Quartiles are when we have our data split in 4 sections. Quintiles is when we have our data set into 1, 2, 3, 4, 5 sections. And then deciles, as another common one you see, is when we have our data split into 10 equal sections, right? So deciles are something that you see a lot. Quintiles are something you see a lot, but the IQR is the inner quartile range. It's breaking our data into the 25th, the 50th, and the 75th percentile, the first quartile, the third quartile, right? And it's just simply looking at what's the range between the first quartile and the third quartile. So again, one single outlier might have a much more substantial impact on the range, but once we start grouping things together in quartiles, then the inner quartile range isn't quite going to be influenced by outliers as much, but it's still going to tell us something about how spread out our data are, right? Variance, standard deviation, taking those in turn, right? Again, we're differentiating between a population value and a sample value, right? If we know all of the values in the entire group, if we know every single observation in our population, then we can calculate a population variance with this equation on the right, right? So for this equation on the right, we've got in our numerator, what are we doing? In that parentheses, we say that that's a mean deviated value. That's a fancy term for saying, what are we doing? In our parentheses, we're taking a single value and we're subtracting whatever the average is. So this value in parentheses, if it's a positive value right here, that means that our one observation is above the average. in the parentheses, if the value that we calculate is negative, it means that our one observation is below the average. We're doing summation, right? So we're taking every single data point, every single observation, and figuring out how far above or below the mean is. And then what are we doing with it? We're taking that mean deviated value and we're squaring it, right? It's raised to the second power. So we take every single observation, figure out how far it is from the average, square that, and then what? In the numerator, or that's what we do in the numerator. In the denominator, we're just dividing again by the total number of observations, right? And so it's in a sense measuring the average of the squared mean deviation of our observations, which is a lot of words to really just say. It's going to tell you how spread out your data is, right? If your variance is, if you have two different data sets and one has a larger variance, it just simply means that there's a bigger spread to the data that has more variance. The sample variance has nearly the same structure to it, right? So notice instead we're still looking at each observation. We're doing a summation for all of the observations in our sample. We're taking each of those observations, but now what are we doing? We're not subtracting from the population mean, we're subtracting it from whatever the sample mean is. Not a big deal. We're still doing the sample mean deviated value, squaring it, but now this is a key difference, right? Is we are dividing in our denominator by not n, but n minus 1. That's probably something you remember from your basic statistics class. Real quick, can we fly over to some data and check that out? So I've pulled up a couple of earlier data sets. Which one do we want to look at first? Let's go ahead and look at the monthly sales stuff. Okay, so I've got my monthly sales stuff. How do I calculate, right, what have we talked about so far? We've talked about some means, and we've talked about some standard deviations, some medians, and some modes. Again, in Excel, there's a number of different ways that we can try to get that. The first place we're going to start is let's go ahead and do some formulas. So again, right, if you've got the if you have your data, let's just look at the average of column B, right? So formulas, a lot of these things that we just talked through, a lot of these different statistics, they've got formulas for them in Excel. So if you hit the equal sign, right, this is one way to do it. A good start is just start typing out whatever it is you want. So we want the mean, and it didn't bring anything up. That's kind of a surprise. What's another name for the mean, though? Average, right? And I see I've got an average one there too. And again, it's got a little description right there that I can focus on. Returns the average arithmetic mean of the arguments, which can be done. So right. So yes, sure, that's the one that we want to do. Whoops, sorry. We want the average. Average down, and then I hit the tab button to bring it up. And all that it's looking for the average is simply right the total. Array of data that we want to take the average of. So these are the sample sales for different months for product A. Straightforward, the average is $81,098. And again, I can take that formula and I can just drag it right, and what I've got, take that and drag it right, and that tells me something, right? I can instantly see something about, on average, what the monthly sales are between these products, right? So it tells me some information, and we could even label this, right? So go ahead and do average, right? So I've got the different average, and it tells me, on average, which product has the highest monthly sales. Who is that, right? Notice that's product A. Does that mean that every single month product A had the highest sales? No, actually, look in January, right? Product E actually had higher monthly sales in January than product A, but on average, product A had more higher monthly sales on average, right? It's a measure. It's not the only measure we could focus on, but it's a measure, right? Okay, so one way that we could do that is like that, right? Let's go ahead and pull all that data out and do it a different way, right? Alternatively, I've got my little formula. I clicked on the formula, the function button right up there, and again, I can type in, or some of the common ones, average, and again, it just same thing, but it just brings up a dialog box. It's asking where do I want to have my average from, and it made a good guess on where I'd want it from, and it already shows what the calculation is. Sure, I can do that. And again, it's a little temperamental here, but I can drag it to the right, and that's pretty straightforward, right? Alternatively, there's a number of different ways that I can pull out this. One of the things that I'd like to do is under the Insert tab, you may see, and I got to shift this over to the right. Under the Insert tab, far to the right, do you see anything at the edge of your screen, at the edge of your Excel? If you're like me, and when you bring up the Insert tab, not the Insert tab, sorry, the Data tab, if you don't see anything right here, we've got to add it, right? So there's some pretty simple, we're going to do some add-ons, but follow with me right under this, not the Save button, but the File button. It brings up some options, and below under Option, and then on the left, Addons. You only have to do this once in the Addons. Should bring up a screen something like this, and the button Go brings up different add-ins, and do those three. Once you've done those and they've taken effect, then under your Data tab, you should have had some kind of change there. I think I just went a little bit too quickly, but that process that I did should have produced under the Data tab, Data Analysis and Solver. And so those are two useful little add-ins. I honestly do not know why Excel doesn't have these built in, and there's so many other things built into it, but those add-ins. Solver is something that we're going to look at further down the road. I wanted to click on the Data Analysis. Under the Data Analysis, there's a number of different things that we're going to look at throughout this semester, so real quick glance down that list. And one of them is descriptive statistics. So if you click on that descriptive statistics, it brings up a nice little dialog box that looks similar but a little bit different than the one that you had earlier, right? So again, our input range, that's simply where our data is, and we can say our input range, I didn't select the right one, our input range is that. Actually, I don't want to do that. Let's go ahead and select B3 through B15, and because I selected that first row is a label, I'm going to select label. Oftentimes, right, if you don't select label, it'll just call it variable 1 or variable 2, and it's much better to put labels on it. Notice you've got a couple of different options. Let's just click on summary statistics, and you can either put it in a new worksheet ply, or alternatively, you can select where you want it. And let's go ahead and stick this right below the data, and output range was right below the data, and I meant to click OK. I think it clicked cancel, and it brings up a number of different things that we're going to look at, right? So the average, the standard error, the mean, the standard deviation, sample variance, skewness, kurtosis, the range, the minimum, the maximum, the sum, the count, right? It's got a whole bunch of different stuff, right? But notice this process, it only did it for A. I can't take these formulas and copy them to the right. That doesn't work. It just copies those values, right? So again, this descriptive statistic option, it gives you a whole lot of information all in one sitting, but it doesn't allow you to be able to manipulate that formula or put that formula somewhere else. So again, there's some advantages, some disadvantages to this, but I wanted to make sure that we did have that piece in the back of our mind. One other way that I wanted to show you, a very quick way to calculate an average, is, right, so I've got my cursor, and if I position I have the cell highlighted right below a series of data, a column of data. Under the Formula tab, right, there's some quick links, right? So this second from the left, right, notice it's got a drop-down menu, and it's got a whole bunch of common functions, including average. If I just click, sensitive, I clicked on the wrong thing with this pen. Average, right? Nope. I don't know why this is not doing this. I think it's just the sensitivity. All right, so data, formula. Doing my select, I'm very carefully going to select average. There we go. And what it does is it just automatically grabbed that whole column of data. Really quick, one click did it. And then again, I could, I could take this data and drag it to the right. I can do my copy and paste to the right. Lots of different ways for me to do this, right? So my measure of central tendency, my first one, average. Great. What was the second one we talked about? Variance. We didn't quite get to standard deviation, but let's go back and talk through that one, and then jump back to this Excel and just talk through how to do that one real quick. I think we can spend just about 2 seconds on this, right? So again, another way to talk about how spread out my data is, other than the variance, is the standard deviation, right? Population, sample, but it's pretty straightforward. The standard deviation, all that you do is just take the square root of the variance, right? So again, the symbols that we use commonly, we've got sigma, the Greek letter sigma for the population, and then S for the sample standard deviation. But again, the difference between variance and standard deviation, the variance is just the square of the standard deviation, or the standard deviation is the square root of the variance, right? So before I want to click over and talk about Excel, I've got this little question here to remind myself. Do you know how to create a formula like this in Word? This is going to be useful for later in this class. So let's go ahead and bring up a Word document and then talk through how we would create a little equation like sigma equals square root sigma squared. Okay, so in a Word document, an easy way to create some mathematical notation, right, is under the Insert tab, far, far, far to the right, you should see, far to the right under the Insert tab, you should see something called Equations. And if you bring up Equations, it brings up this little dialog box, and at the tab in this subthread, right, there's a number of different options that you can do that Word gives you some pre-formatted equations, but you can also just start typing. If you recall, that equation that we had was it had the sigma term, right? So if I just type out the word sigma, it doesn't do very much, right? But if instead I did is that a forward or a backslash, right? I always get confused on the forward and the backslash. I think that's a backslash. It's the one that's directly above the enter key and below the backspace on most keyboards, right? With this slash, then you can write out the Greek name. It'll convert your name to the Greek letter, right? So we did sigma, we've got beta, delta is another common one that we do, right? Easy way to just do some equations, right? But again, all that we've got is sigma. And say that we want to talk about the sigma or the variance on income, right? So in order to use superscripts or subscripts, we can either use the caret that's above the 6 for a superscript, or we can use the underscore, which is right next to the 0 key, right? When we do underscore, right, I can write out the word income, and then when I push the enter key, it pushes everything that was to the right of that underscore as a subscript, right? So this is my shorthand notation for the variance of income. What is it equal? Actually, we didn't do variance, right? We want not the variance, but we wanted the standard deviation. So I go back to mine, and I've got my slash sigma. The sigma is equal to, let's see, square root, SQRT. Nope. Let's go ahead and do the slash SQRT. Yep, there we go. And again, it was the square root of sigma squared, so I'm just using caret 2. And then it automatically is going to do a nice little job. And notice that I was typing, and you notice what it was happening, right? It was so I've got my little square root symbol initially right there, right? And then I'm typing everything to the right, and it's when I hit the space bar. It's when I hit that space bar earlier that it carries that square root symbol above everything that I've been typing out. So again, right, just little quick introduction of how to do a little bit of equations in Word. Later on in this class, you're going to be doing some stuff where you're going to be writing some reports up in Word, and you're going to want to use equations. This is just a nice little way to create equations and mathematical symbols in Word that look really, really good in terms of their presentation. Again, under that data tab, there was the data analysis to the far right that had the very, very basic descriptive statistics, and it brought up this whole thing. But to do formulas, right? Let's do the two. We've got the variance and we've got the standard deviation, right? That needs to be a little bit wider, right? So I can double click between the A and the B column to make it automatically wider. Not surprisingly, variance Hey, actually, notice when I start typing out VAR for variance, it brings up a couple of different options. And notice, right, notice equals VAR, that it gives me a couple of different options. VAR.P, VAR.S. What's the difference between some of these different types of variance? Notice this one that has a little error code. That's with earlier version of Excel, but the .P and .S, can you see the difference in the descriptions? It does calculate the variance, but one is based on a sample and one is based on a population, right? So let's go ahead and assume that we've got our sample values, and if we highlight everything that we care about, it's going to return back what the variance is. And again, right, I can take this formula and I can copy it to the right one more time. Copy it to the right. And it will, I can look at those different values and, oh boy, let's see. Let's look at some of these, right? So product A had a variance of 465,748, 917,488, 139101, 105939418, 63467. Think about that, right? So my goodness, there's different values. What are those different values telling you, right? So fundamentally, right, can I ink on this guy, right? So how would you interpret the different values of variance for the different products? Right? They're all telling you something about the measure of how spread out your data is, with bigger numbers telling you that the data is more spread out, that the average mean deviated value is higher for those products that have the higher variance. Pretty straightforward, right? Let's go ahead and get back to calculating some stuff with standard deviation, right? Standard deviation, again, ST for standard deviation, and it starts bringing up a whole bunch of different things that might be useful for you, and it's got STDEV.P.S. Perfect, right? So let's go ahead and do the standard deviation, where we've got, select all of the data, standard deviation. These numbers are probably going to be easier to tell which has the bigger standard deviation and which has the smallest standard deviation. Yeah, these numbers are much easier to get your mind around and identify which is the big one and which is the small one, right? What's the relationship again? The standard deviation is supposed to be the square root of the variance. So if I take the variance, if I take the square root, SQRT is the square root formula of the variance, yep, not surprisingly, I get the standard deviation. Or alternatively, if I took the standard deviation and I squared it, not times 2, but raised to the second power, I get the variance, right? So there's this pretty straightforward connection between the two. There's one thing that I want to point out that's a little bit technical, hopping back to the equations. There's one point that I want to calculate, or that I want to point out earlier, that has to do with the units. So on the variance, notice, regardless of whether we're doing population or sample, notice what are we measuring in the vertical, or in the vertical, in the numerator, right? In the numerator, we were looking at each of the values subtracted from the average, right? The mean deviated values. When we were looking at the sales data, what was the average sales being measured in? Dollars, right? And each of the observations was being measured in dollars. We were taking a dollar difference, which the unit in the parentheses was dollars, and then what were we doing? We were squaring it. The units on the variance are dollars squared. Specifically dollars squared per month, right? And again, it doesn't matter whether we're doing the sample or the population, the units on the variance were the units that we used from the average, right? The units that we used from the average would have just been dollars, and then we are squaring, so on the variance, we are squaring that dollar amount. But notice, when we have the population standard deviation or the sample standard deviation, either one of these standard deviations, what the standard deviation does is it takes, and it does the square root of that. What are the units on standard deviation? They're being measured in the square root of dollars squared. The units on standard deviation are the same units that we use for the average. That's one of the nice things, right? The mean and the standard deviation have the same units. So let's hop back to the data again and reinterpret those. So again, seems a little strange to think about this, right? But the product A, 81.98. What are the units on the average? That's $8,198. The variance is, oh, this is messy. Where's my comma? $465,748 squared. That sounds like nonsense, right? Standard deviation, though, is just $682. So again, the average and the standard deviation are using the same units. That's going to be useful in another measure that we're going to talk about in just a little second. You may have heard of the empirical rule before. This is something that usually most people from their earlier statistics class it sounds familiar to them. We think about number of observations, specifically the proportion of observations or the percent of observations that are going to fall within 1, 2, or 3 standard deviations of the means, right? So the classic example of this is if we've got a normal distribution, right? If we look 1 standard deviation out, how much of the data is going to be captured 1 standard deviation on either side of the mean, either above or below, right? According to this thing called Chevyshev's theorem, right, that's going to be about 68% of the data. If instead we're looking at 2 standard deviations out, so I look at 2 standard deviations out, that's going to be about 95% of our data, right? And a normal distribution is usually a really good way to conceptualize this thing, right? If I'm going to look 3 standard deviations out from the mean, that's going to be capturing, my goodness, according to this empirical rule, about 99.7% of our observations, right? So this empirical rule is just based on a little bit of math that's beyond us, but it's still useful for a lot of the things that we're going to do later in this class to think about in general how closely the empirical rule might fit some actual data. We have a very small sample, but let's go ahead and go back to, actually let's pull up a different data set. Let's go ahead and pull up the sales transaction data and talk about that for a second. Okay, so I have this sales data. I want to look at column F, that is the amount, right? So these are dollar amounts. And let's go ahead and insert a column right to the right of that thing, right? Actually, let's go ahead and insert a couple of different columns right to the right of that. So I'm clicking on the column and then I'm right-clicking and doing insert. If you're doing a Mac, I'm not quite sure exactly the same set of clicks for a Mac. It's been a while since I've used that. But we've got this whole column, and again, to scroll up and down, my shortcut keys are Control up and down are going to jump to the bottom and top of wherever my data set, list of data is in a column, right? So in column F, I've got an F3, I've got the word amount, and then my data starts in F4 and goes all the way through F475. So real quick, below that, can I calculate the average amount from all these sales transactions? Again, a lot of different ways to do that. Average is one easy way to do that. So I click on that button, hit the period, and then I can jump all the way to the top of this thing, and I've got what my average is. The average amount of spending was $39.95. Let's also calculate real quick the standard deviation so that we get a sense of how spread out the data is. Because in order to investigate the empirical rule, those were the 2 pieces of information that we needed, right? We need to know what the average is, and we need to know what the standard deviation is. Oh my goodness, the standard deviation is 57.32. I didn't try this out with the data before. I just thought I'd bring up a data set and we'd start trying it, and that's going to be really interesting. All right, so let's figure out. We've got again, this is important, in cell F476, I have the average, and in F477, I have the standard deviation. So what I want to do is I want to see the empirical rule was saying that the difference from the mean is within one standard deviation. It didn't matter if that difference was a positive difference to the right or a negative difference to the left. Let's calculate in column F what the mean deviated value is, right? So I've got in row 4, my first observation, I've got F4 has that value of $20.19, and if I subtract $20.19 from, let me scroll all the way down to the bottom of the list and do $39.95, where my average is, hitting enter is going to return the mean deviated value. Ooh, it's in red. That's because if you highlight all of this under the Home tab, it looks like it might be trying to do some kind of dumb accounting sort of thing. No, I didn't mean accounting's dumb, right? But it might be trying to do some kind of accounting format or currency format. We want it to be the negative 1976. Can you interpret what this value of 1976 represents? So the question is that 1976, that's the mean deviated value, right? If we go ahead and copy this formula down the entire list, it's going to mess up, right? What we need to do is we need to lock in that average. We want that to be an absolute, not a relative one. So again, move your cursor right so that it is in the middle of the F476, and then if you hit the function key of F4, that's a way to lock that in, right? And so then, right, if I copy this down the list, it's gonna hold fixed that that average amount. And went too far there, right? Remember, when you double click on that, it's going to go down the entire list, and I actually didn't want to calculate it for the last two because those were my overall average and standard deviation, right? But it's got, now I've got in column G, I've got a whole bunch of different values of mean deviated amounts, mean deviated amount of sales. And notice that a whole lot of these guys are negative, and some of them are positive. But it looks like a whole lot more of them are negative than positive. The question that for the empirical rule is this mean deviated value less than the standard deviation? I can actually insert into this an if-then statement. So I'm going to go to the beginning of my equal sign, and I'm going to do an if, right? And it's going to do if, and it's going to hold that calculation that we just did. So if that mean deviated value is less than or equal to, where did I have my standard deviation? Right, it was all the way down at the bottom of my data in cell F477, and that's also one that I want to lock in with my my F4 function key, right? Okay, so what this calculation is doing is saying we're going to calculate this mean deviated value, and if it's less than the standard deviation, let's give it a value of 1. If not, let's give it a value of 0. And so what we're going to be doing with that is, instead of reporting the mean deviated value, it's going to be taking on a value of either 0 or 1. If it's within one mean deviated value, it'll take on a value of 1. In essence, this is like a dummy variable for within one standard deviation. And if I go ahead and copy that down the entire list, then I've got a couple of things, right? Number one, I could go to the bottom of this list. Actually, I better go to the bottom of this list to make sure that it didn't include all the other, it didn't include these last two these last two values that were the average and the standard deviation, right? If I just highlight this whole thing, have you noticed right down here in the bottom of this ribbon that it gives me a couple of pieces of information? It tells me the sum, it tells me the count, and it also tells me the average. Do you recall what the average of a dummy variable would represent? It's telling you the percent of your observations that have a 1, in essence, that have that attribute of being within one standard deviation. Oh my goodness, right? So if I go to the bottom of this list, I could also just take my formula and copy it to the right. Oops, that's putting it as dollars. I don't want it as dollars, right? This is actually a percentage, right? So this is the value of the average of a dummy variable is actually telling you the frequency of the thing that's being identified with the ones. what did the empirical rule say? It said that, right, the empirical rule said that within one standard deviation, it was going to be what, about 67% of our data? No, right? With this data, 88% of these observations in these samples are within one standard deviation, right? So you might want to stop and think for a second. Would you be able to create dummy variables to find within 2 or 3 standard deviations to further investigate the empirical rule? Another very common tool that we can use is called standardizing, right? We can look at standardized values. So to standardize something, that's when we come up with a z-score. And again, this is probably pretty familiar from your Stats 1 class. Little equation, this formula has some things that look familiar to us, right? In our numerator, all we're doing is looking at the mean deviated value, but rather than leave it in the units of dollars or whatever it is we're measuring, we divide it by the standard deviation. So in essence, what the z-score represents is it's counting up the number of standard deviations away from 0. If it's a positive number, it means that the mean deviated value is positive in the numerator, because the standard deviation is never going to be a negative number. If the z value is positive, it means the mean deviated value is positive. It means that the observation is above the average, right? So the z value for a positive 1.25 would be counting up. It would be telling us that our observation is 1.25 standard deviations above the average. If we've got a little normal distribution, could you figure out where a z value of 1.25 would fall, right? Again, if I draw this thing out, if I go 1, 2, 3 is going to capture most of it, right? According to the empirical rule, one standard deviation is going to be about 67%, so 1.25 would be a value that's somewhere about there. And again, it's to the right because it's a positive value, whereas a z value of negative 1.5 would be between the 1 and 2 and to the left because it's a negative. It's 1.5 standard deviations below the average. Why do we ever use standardized values, right? Because again, if we consider a data set, like let's hop back to that sales transaction. Just kidding, let's jump back to the product data set. Let's look for the month of January and calculate the z value for products A and B, right? So I've got product A, I've got the, this is going to be a formula, or the fraction, right? So I've got to have a numerator and a denominator. In my numerator, I take the observation from January, and I subtract out the average of the entire data set for the product, all 12 months, and I divide by the standard deviation. And if I hit enter, right, what it's telling me is that for product A, their monthly sales in January were 0.59 standard deviations below their average. If I take this formula and I just copy it 1 to the right, and again, you can click on this and it verifies that the relative measure of everything was calculating the z value for product B. It's saying that for product B, right, my goodness, look at the value of product B's sales. Much, much lower than product A. However, product B's sales in January were 0.8 standard deviations above product B's average, right? So what this allows me to do is it allows me to compare different data sets that might have different averages or different spreads of their data, but it allows me to talk about a relative position of one observation in a data set compared to the relative position of an observation in a different data set. And sometimes that's a useful thing to be able to do. The other reason we talk about z-scores is that while this is the z-score for an individual observation, that's actually going to be a useful concept for us later on with some of our hypothesis testing and inference stuff we do. Next, one of our last metrics that we're going to talk about is this thing called the coefficient of variation, or the CV, right? So again, pretty straightforward formula for this thing, right? What do? Boy, this kind of looks like the z value, right? It's got an average and it's got a standard deviation, but it's a little bit different. It looks at the standard deviation in the numerator divided by the average in the denominator. Let's go ahead and click back to the product values and carry out that calculation in Excel. All right, so again, to calculate this CV, what is it looking at? It's looking at the spread, which is measured in dollars, divided by the average, which is measured in dollars. And if I copy that across for all of these, think for a second. Is it obvious what the higher values of CV represent compared to the lower values of CV? Think again about what that equation represents, and what does a high value of CV represent, and what does a low value of CV represent? Only very quickly in passing am I going to mention two other ones. I said three because I saw this little number right there. Notice this CS, this coefficient of skewness, it was something that the basic descriptive statistics in Excel produced, that little dialog box, but it's a pretty complicated formula, right? It's got something that's still familiar. It's still looking in our numerator at a mean deviated value, but rather than raising it to the first power or the second power like we've already seen, this raises it to the third power and then divides by the sigma cubed, right? The skewness is a way to talk about how symmetric observations are around a mean. And again, this calculation, I don't think it's that useful, but we want to make sure we understand a little bit about skewness, and we'll talk about those in half a second. The other one that, again, we just mentioned very quickly in passing is kurtosis, right? And so this has to do with how flat or how tall a distribution is. And it also raises to the fourth power. Again, this is something that oftentimes is going to be beyond what we need to do in this class. Though I will point out, if you're thinking about going into finance as a potential major, right? So some of these higher order measures of tendency in a distribution actually become a little bit more useful when you're doing more advanced finance type stuff. So I want to point that out, that if you're going there, you might want to study these later on a little bit more depth. At this point, all we need to do is make sure we just understand these pictures, right? So I've got a symmetric bell-shaped curve. Why do we say it's symmetric? Because if I cut it right in the middle, oops, tried to cut it right in the middle, the left-hand side would look identical to the right-hand side, right? Many times we're going to see observations or see data sets that are not symmetric. They're either going to be skewed left or skewed right. Oh boy, here we go. Question. So earlier we talked about that income data, and I said that income data of U.S. personal income might have a little bit of a skew to it. So real quick, hopping back to our skew pictures, which do you think is more likely a representative of income distribution in the U.S.? One that is skewed left or one that is skewed right? So the other thing that I'm going to ask about this, right, is do you know the relationship between mean and median, right? So the median is the 50th percentile, right? It's right if I were to take my data and I were to cut it right in the middle. So I tried to, in black there, cut it in middle for the median. But now if I tried to calculate the average probably be a little bit, if I've got this skewed right distribution, the average is probably going to be higher than the median. Whereas if it's skewed left, I'm not quite sure. I drew that point in black far enough to the right. Let's put it a little bit further to the right. And then the average is probably going to be somewhere around here. That if my distribution of data is skewed left, the opposite holds, right? The average is less than the median, right? So again, that might have some implications for what you were just thinking in terms of the income distribution. Lastly, we want to talk a little bit about some measures of association when we're not talking about a single variable, but we're talking about two variables together, right? So covariance, I've got two different data sets there. I've got the unemployment rate in blue, and then I've got the real gross domestic product. This is the growth in the real gross domestic product, not the level of gross domestic product. Does it look like there's an association between those two? if you've taken a macroeconomic class. Do you think there's a relationship between how well the economy is growing and what the unemployment rate is, right? We'd expect there to be some kind of negative association there, right? That when the economy is going bad, that the unemployment rate is going up. And when the economy starts growing again, when it becomes positive, that the unemployment rate goes down. Yeah, so maybe that is, right? We've got this long, complicated formula for covariance. That's a nice little thing, but notice what are we doing here in the equation, right? What we're doing is we're taking the mean deviated value of one of the variables, we'll call it x, that could be the unemployment rate, and we're multiplying it by the mean deviated value of the other variable, y, in this case, real gross domestic product. And so what you can think about is if you have a situation where the economy, that was our y, if our economy is not doing well, if there's a recession, that we think that its mean deviated value would be negative, right? It's negative because it's below the average. Whereas when the economy is doing poorly and is below average, what's going on with the unemployment rate? More than likely, the unemployment rate is going to be above what the average is, right? And so if we take a bunch of these below average GDP values and multiply them when we have above average unemployment, which is the relationship we'd expect, we're going to have a bunch of values that are all negative values, right? Alternatively, what about those times when the economy is doing well? When the economy is doing well, we're going to have positive mean deviated values of GDP. And when the economy is doing well, the unemployment is going to be falling below its average, right? So we've got, again, we're going to be multiplying a bunch of negative values to a bunch of positive values. This covariance measurement is going to be overall negative when these two variables have a negative association with them, right? So you've probably seen something like that before. Oh, I forgot that I had this little graph. This takes these data series and it presents them as a scatter plot rather than as their time series. And notice, right, one of the nice things that we can do is if we just cut this in 4, do you see more variables in certain quadrants, right? So in this top quadrant, I've got measuring, this is GDP, and then this is the unemployment rate. So it looks like up here in this first quadrant, we've got positive GDP and positive unemployment rate. So that's 2 positives, and there's some observations there. In this bottom, or this top left quadrant, we've got below average GDP and above average unemployment. We've got some observations there, but we've got a bunch of positives and negatives. Down here in this quadrant, it doesn't look like there's a whole lot of them, and some of them have pretty small values, right? That we've got below average GDP and below average unemployment rate. Those would produce a bunch of, when we multiply those mean deviated values, those would be a bunch of positive. And then notice this sucker, right? In this quadrant, we've got a whole bunch of observations. Those are going to be a whole bunch of numbers that show up in our numerator. And what does this big dominating quadrant have? It's got above average GDP and below average unemployment. And so, yep, we'd expect to see a whole bunch of those negative products dominating this summation. The covariance is going to be negative, and it's basically saying that there's this negative relationship between. And again, so if I tried to do it, but let me clear out all those quadrants before I say that, right? If you just looked at the pattern in this data, does it look like the pattern in this data has some kind of downward trend to it? Looks like it does. Maybe I drew it a little bit too strong of an association there, but it looks like there's some kind of downward trend to it. The covariance is one thing, but notice, right, we might get some really strange units. If we're talking about the unemployment rate and the GDP rate, we're going to be looking at some units of percentage changes. What a nice way to abstract from these units is this thing called correlation that, again, you've probably seen before, measure of linear relationship between two variables. And again, this is independent of the units that's being measured. Population and a sample correlation coefficient, all that we're doing here, right, is we're taking our covariance that we calculated earlier, and we're just simply dividing by the product of the standard deviations. What this does is this is going to normalize it between a value of -1 and 1. It's going to fall somewhere between -1 and 1, and it's independent of. It does not depend on the units that are being measured, so we could just calculate this statistic for any set of data, and we're going to get some number between -1 and 1. The closer it is to -1, the stronger and the more negative the association. The closer it is to 1, the stronger and more positive the association is between two variables. So again, right, so these correlations, you've probably seen them before. Total expenditure on health and total income, right? So this looks at a number of different counties in the US, and it just looks at the wealth, or not the wealth, but the income in a county and how much people are spending on healthcare on average, right? And it looks like there's this really strong positive association, and you can think about there's this statistical positive association, but could you also think about whether or not there was some kind of story about a correlation, not a correlation, but a causal relationship between these variables? Does it make sense to explain why? What are the mechanics for why, when there was more income, we'd expect to see higher expenditure on health? And again, this correlation, it looks like this has a population coefficient. Notice the notation that I'm using R. It looks like it would be a value that's pretty much close to 1. There's another thing from Stats 1 that you probably are familiar with. Do you remember the R squared? Literally, the R squared is just taking these correlation coefficients and squaring them, right? So I said that the range of the correlation coefficients was -1 to 1. If we square that, if it's got a strong negative correlation, it's going to be close to 1. If it's a strong positive correlation, it's going to be close to 1. If it's in the middle where there's not really a correlation between the two, that's when it's 0. So what the R squared does is it tells us the strength of the relationship between two variables. The number itself doesn't tell us whether it's a positive correlation or a negative correlation. It just tells us the strength of the relationship, right? And I've got, right, this one would clearly have an R that's some kind of negative value. Maybe -0.6 might be a reasonable value or something like that, right? Customer satisfaction and how long it took to resolve an issue. So we clearly expect, right, the longer it takes to resolve an issue, lower customer satisfaction. We'd expect to see that kind of negative correlation. So again, that's the end, but that kind of just touches on some of the basic stuff that all of that should have been pretty much a refresher from your basic statistics class.